Okay, brilliant. We have reached the last video of chapter 9 on ordered indexes. We are in the midst of our discussion of how ordered indexes play a role in MonetDB, and we have just talked about the order indexes in MonetDB. There's more types of indexes in MonetDB. There is the so-called column imprints, and there is the normal hash table that you would expect inside a modern database system. But I would like to talk about a different, very neat idea that has been implemented inside MonetDB, and I think that is really unique. And it also relates to the evaluation of queries that are order sensitive, in particular to the evaluation of range predicates. So it's a good fit for this particular chapter, and it makes for a great final video, I would say. So let's see, what about column cracking? All right, so with column crackers, MonetDB introduces yet another ordered index structure into the system. These indexes are not built up front or built in one shot, but they self-organize and rearrange themselves when they realize that the particular queries occur again and again in the query workload. It's an adaptive index structure that indexes those parts of the data that are really relevant for your query workload and leaves aside and does not invest many CPU cycles into those partitions of the data that play a lesser role in your query workload. So this is really well invested CPU cycles. These cycles are invested into those parts of the data that make a difference for your query workload. Okay, so such a cracker index is being built when it comes to the processing, to the evaluation of range selection predicates. Range selection predicates like, let me nudge that pointer a bit, like this one. Okay, so we're looking for column values A that lie between two border values, range border values low and high here. Okay. While we process these range predicates, we can opt for the optional maintenance of a cracker index that is particularly built to support range predicates on the A column, of course, but it's actually, this cracker index is more specific even. It's a cracker index that is fine-tuned and it's really geared and specifically made to evaluate queries in this particular range of the A column. Okay, in such a cracker index, if we look inside it, and we will do so on the next slide, we will find that the A values in the low-high range, in the range that was just being queried and that appears to be relevant to our query workload, the A values inside this range are indeed stored physically continuous in ordered fashion. Okay, right. So we will find those values that are relevant to our query workload. We will find them physically contiguous, so they fit into few cache lines, maybe even a single cache line, a very small portion of our cache, and they will be sorted even. Okay. Other parts of the column A that may lie outside this particular range are of course also stored in the cracker index, but we will not invest time in rearranging these values and in sorting them, for example. Values outside this range first have to prove that they're indeed relevant to our query workload. If our query workload continues to focus on values inside this low-high range, then the ranges outside the low-high range will not be considered anymore and not be sorted, for example. While if we have further queries that hit the lower-high range, or maybe are inside the lower-high range, we will indeed refine and make the index even more granular in these particular portions of the data. So we will really invest in the hot query intervals, the hot query ranges, and leave everything lying by the side. Okay, this is an idea that was called database cracking by a team or a sub-team of the authors of the MonetDB system itself, has been published 2007, so it's 13 years but now. By now it's still a more exotic idea, but it has proven to be really worth it and really a nice technique. So let's look at how this works. Okay, so we would start with our original BUT, the original BUT A, let's say. Okay, so the A values in this column BUT, they would be subject to range predicate evaluation. And as you can see, this is a completely unordered. It's neither sorted nor ref sorted. The values inside column A are unordered. So without any further order index support, all that we could do now is to do a full scan of the entire column when we need to evaluate predicates of this form. This would be one of these range predicates that we were talking about. Find all the A values between 5 and 10 exclusive. That would be one such range predicate. Evaluating this on this unordered column would call for a full scan. Okay. If we opt for the creation of a cracker index, then we can do so. We can build this cracker index while we scan this column from top to bottom to find the matches. Right? We will do this and of course find all the matches to build the selection vector for this particular predicate. Okay. But on the side, we will also build a cracker BUT. Again, the index comes in the form of BUTs themselves, not in the form of trees or so on. It's just an array of values. This is something that we can particularly efficiently access inside our system, and that's the representation that we choose inside MonetDB. All right, so while we scan this column, we can, on the side, we can create this cracker BUT that will serve as an index structure. And you can see that the values that fall inside this queried range between 5 and 10 exclusive, they are indeed found here in the cracker BUT, and they are indicated as a slice, as a contiguous range inside this cracker BUT that contains all the values greater than 5 but less than 10. Okay, so that would be the answer actually to our query. The values or the rows in the slice S2 are indeed the answer of our query. Okay, everything around this interval, around this slice, is of course also present in the cracker BUT, but well, it remains unsorted because it still has been of no interest in our query workload, and so the values are present, but we just qualify them as those values less than 5, so just less than the values in the result slice, and the values greater or equal to 10, so they lie just outside the slice. The slice S2 that was interesting to our query evaluation. We've built a slice S3, but as you can see, inside slices S1 and slices S3, we do not bother, we do not sort stuff. And well, yeah, that's the output, the side output of our selection evaluation. All right. So now the next time the next query QJ comes, we can build on this cracker BUT because it's already present, and we can of course exploit that we know, for example, that slice S2 holds all the values inside this range, and this range falls into this queried range here. So we know that all of the values inside this particular slice will indeed be a match, and they could be part of the result immediately. Okay, the ranges of our new query QJ, they also hit this particular slice, the S1 slice, and we would refine it at this particular point. We would refine it into this state where we discern between the values that are less than the lower range. 3 is our lower range here. So values that are less or equal to the lower range and thus would fall outside our queried range would be held in this particular slice, and another slice would hold all the values that are inside the range. Okay, then there would be the old slice S2, it's now called S6, that is left untouched here. Okay, we would just have that, and our upper range border hits the old slice S3. So we would refine it, we would split it, and we would discern between the values that are greater or equal to 14, which would lie outside our queried range, and those values larger than 10 or equal to 10, which will lie inside the range that we have just queried. Okay, so the entire result of our query would be this. These three slices would make up for the result of the new query. Okay, outside these result slices, you see that the values are still present, but we do not care about them. We just let them lie here unsorted, while there is indeed a sort order established on the values inside the interesting ranges here. Okay, so we now even know more about the location of potentially interesting border ranges inside our crackerbutt. And of course, the more queries come, the more we can exploit this fine granular knowledge about the range borders and piece together our results from either existing slices, existing intervals, or by splitting existing intervals into new intervals, and thereby refining the cracker index in exactly those parts of the data that are relevant for our query workload. Okay, a few more notes on this column cracking. If you look at it closely, then all the values in a particular slice as I are smaller than the values in the subsequent slice, in the slice as I plus 1. So let's switch back here and let's look at the values inside slice S6. These are 6 and 8. They're indeed smaller than the values in the slice S7, which is 12, 13. All right, so there's an order of values regarding subsequent slices. Okay, if the slices are refined and refined and refined and then reduce their size and then eventually reach size 1, so this would be the minimum slice size that we can achieve, then you would see that the column is indeed completely ordered. This is something that would be rather uncommon in the practical cases. This would mean that all slices are interesting to your workload and all slices are indeed relevant to the evaluation of your queries. This is probably rather uncommon because you would experience skew or would observe skew in the queried ranges that your query workload finds interesting. So particular parts of the data will be of particular interest, and we will focus with our queries on that, and we will in a very fine granular fashion will split intervals and slices in this particular part of the data, but other parts of the data may be completely untouched. All right. Well, of course, the end result might be a completely ordered crackerbutt index. Okay. Only in the first step, we would copy the source butt data from source butt R into this crackerbutt index. From then on, we would just reorganize the crackerbutt index and leave the original butt alone. All right, so that would be the step in which we copy the data into the crackerbutt index structure, and we would then reorganize internally inside the crackerbutt index structure and leave the source table alone. All right, we have talked about slices already when we introduced the tactical optimization for algebra select. Okay, so piecing together such slices to form the overall query result is really efficient in MonetDB. If this makes for the entire result of our query QJ, then that would be just a particular view of the crackerbutt index, a view that will disregard everything above this border and would disregard everything below this range border, and everything inside here in this slice would be considered part of the result. We could just generate a view of the crackerbutt index, a view that would start here and a view that would end here, and would disregard all the rows outside these particular view rows, and we could generate a query result without even copying those rows out of the cracker butt into an extra query result. We could just have a particular view of the cracker butt to represent the result. This is really efficient and almost cost-free, no data movement involved here. Okay, and one very nice thing that I mentioned in the very beginning of the discussion of the slide that we have just seen, that is this cracker construction and the cracker reorganization, this shuffling of values inside the tail of the cracker butt, is something that can be performed very efficiently while we scan the butt. It can be even performed in situ. In situ means that we don't need any further temporary storage to perform this particular reorganization operation inside our cracker butt. We would just replace values and shift values around inside the storage space of the cracker butt cracker butt column itself. The algorithm that can be used to do that is reproduced on the upcoming slide here. On this slide, it's given only for the very simple case that we are operating with this half open-ended range query. So it's a query with an upper border high, but not a lower border low. You can look for the details of the more complicated cracking routine for such two-sided range predicates in the paper that I've shown you in the footnote on the previous slides. Here we can briefly discuss the case where we have a half open interval and we would like to rearrange our butt such that it properly reflects this particular range query. So the result of the cracking would be a butt, of course a butt. A cracker index is represented as a butt, and it would have two slices or two ranges. One with all the values that fulfill the predicate are in the less than high slice, and one with all the values that are outside this particular slice. Okay, so that would be the result of the cracking in two distinct slices here. Okay, so how would we go about that? Well, we would have a routine that of course works on this butt A, and we inform it about the upper end of the range that we are querying. This defines the border between the two slices. Okay, and we would start our exploration in the butt, our scanning of the butt at offset start and end in the butt. Probably this will be the beginning offset and the end offset, the last row of the butt, but they need not be. Start and end could point somewhere inside the cracker butt so that we can only reorganize parts of it. Okay, so we would maintain two pointers, a start and an end pointer into the butt, and we would move that start pointer from the beginning of the butt towards its end. Okay, and our purpose or our aim there is to look for values that are larger than high. Such values would have to be at the end of the butt. Currently, we are in this part of the code, we are scanning the beginning of the butt. So if we meet a value that is larger or equal to high, then it should be moved to the end of the butt. Okay. Well, if you don't find such a value, if you encounter very small values less than high that belong to at the beginning of the butt, then we would just do nothing and just increase our pointer and continue with our search until we find such a rather large value. Okay, when we find such a large value, we will then start our scanning from the end of the butt. We will start from the end of the butt and look for values. So we would go this way and look for values that are indeed less than high. These would belong to the beginning of the butt. Okay. If we do not find such values, then we will just continue scanning. But at one particular point, at this point, we have found a value that is indeed less than high. Here above, we have indeed found a value that is larger or equal to high. We will just swap these two values in situ, need no extra storage space there. We will just swap these two values so that the larger value has its place at the end of the but, the smaller value had its position at the beginning of the but, and this would be one step towards a correct cracking or slicing of the input but A. Once we've swapped, we just move our pointers because these two elements have been processed currently, well, yeah. Then we would just return to the top of the loop and continue our scanning for values at the beginning of the but that are just too large. Of course, we would end the loop. You see these conditions here. We would end the loop once the end and the start pointer cross each other. This is an indication that we have processed all the elements in the input but. Okay, I think I brought an example with me. I brought an example with me that shows how this pointer movement and the swapping of elements could look like in a column. So here we go. This is one such sample column. It's just an unordered range of values. Okay, and well, we would like to rearrange it. We would like to crack it in two regarding this selection value high 5. Okay. Okay, so what we would do, we would establish start and end pointers. This would be the start, this would be the end pointer. So we are cracking the entire column in this particular example. All right, and then we would start scanning. Start scanning from the beginning of the but and look for values that are indeed 5 or even larger than 5. Okay, so these would need to be placed at the end of the but. Okay, 17 is indeed such a value. 17 is indeed such a value. So let's scan from the end of the but. Let's move the end pointer and let's find a value that would indeed belong to the beginning of the but. All right, and we would move the end pointer. The 12 is something that can reside at the end of the but. That's fine. The 4 here, we move the end pointer and find the 4. This should actually belong to the beginning of the but. So we have two values, 17 and 4, that actually should change their positions. And we would swap them and we would end up with something like this. So 17 is gone, but 4 is there now. Okay, 15, 13, 17, 12. And then we would move our pointers, our start and end pointers, so that we can continue processing. So that would be the situation after the first swap. All right, so then we would continue scanning the column and would look for values that are larger than 5 and or equal to 5, and this is not such a value. We would move our pointer to here. And 8 is a value that regarding the border 5 should actually be in the lower slice of the but. Okay, so let's check if we find a value that we can swap with the 8. The 15 here would be one value that should remain where it is. Okay, then we would hit the 2 here. And this is indeed a value that should be find its place in one of the in the upper slice, in the slice of smaller values. So it's now time to swap again. Okay, so 4 and 3 remain. 8 is replaced by 2. The 6 is 2 is replaced by 8. That's the swap operation performed. Everything else remains the same. And we would then move the start and end pointers. They would actually meet here. If you look at the code, then you would find that now indeed the code would swap the element at position start and end in this particular case. So 6 would be replaced by 6. That's fine. Then the start and end pointers would move further and end up in this situation. So now the pointers have crossed each other. This would be the indication that the cracking has been done. the cracking border, the slice border, is actually found just below the E pointer, the end pointer. So that would be the border that we've indicated, that we found, and that would continue. That would complete the cracking. So these are the values that are less than 5, and these are the values that are larger or equal to 5. Cracking done. Next time we can rely on the presence of these two slices when we process queries. All right. So much for that. This is our discussion of ordered indexes in chapter 9 of the DB2 course. This has been one of the core of the major chapters in this particular course. Much more cool stuff is ahead. For example, how to marry the query evaluation process and the exploitation of indexes. So indexes are of no use if they are not used cleverly in the evaluation of queries. This is exactly what we're going to talk about in chapter 10. So I hope you will be around then. I will start to prepare the slides for that now and rework the slides so that they are ready for your consumption in a few days. So take care, see you then, and have a nice time. Bye.